Welcome to Lyons Township High School AP Physics. Today we got an example involving electrostatics. Specifically, we've got three charges and they're in a pattern. They're not lined up, and we're going to find the net force acting on charge B due to the other two charges, A and C. So you might want to spend a moment copying that down. All right. So we're going to find the net force on B, and I'm going to start by, well, for finding net force, it often involves drawing NFBD. So we're going to look and see what the other two charges do to B. So what's A going to do to B? Well, A is a like charge to B, so like charges repel, aka push. So A is going to push on B. That'll be a force this way. That's the force of A on B. What's C going to do to B? Well, C is an opposite charge to B, so C is going to pull on B, opposites attract, so that's going to be a force down. That's the force of C on B, okay? Well, we're going to now calculate those two forces, the magnitude of each one. So we'll do the force of A on B, which we're going to use Coulomb's law, F equals K Q1, which is QA in this case, times QB over the distance from A to B squared. And we have all those numbers, so K is 9 times 10 to the 9th, QA is 20 times 10 to the negative 6th, QB is 30 times 10 to the negative 6th, and they are half of a meter apart. And if you plug and chug all those numbers, and you might want to give that a shot, make sure you can do it in the calculator, you get 21.6 newtons, and that is to the right. So I'll draw the little right arrow just to remind me of that. How about the force of C on B? All right, so the force of C on B is going to be K QC QB over the distance from C to B squared. So K is 9 times 10 to the 9th. QC is 40 times 10 to the negative 6. QB is 30 times 10 to the negative 6th, all over. How far is B from C? They are 0.7 meters apart. Make sure you square your radius. And there I get about 22.0. And that force is down, okay? And again, I write the arrows to kind of remind me of that idea. Okay, so now notice too that I didn't put a negative sign in for QC. I don't use the negatives, okay? I've already used the negatives to figure out which direction the forces point. You are done with the negatives. The only negatives you need to keep track of are, well, if you have a negative exponent, you got to have those in there, but you're done otherwise with negatives. All right, so now I got to find my net force. Well, this is going to harken back to our old friend, the vector, all right? So you got one vector pointing right, one vector pointing down. You have to vectorially add those together. So I'll draw a little vector triangle. We've got 21.6 newtons to the right. We've got 22.0 newtons down. We started there. We ended here. That is our result. If you're trying to find net force, you need to know both the magnitude of that vector and the direction. For the magnitude of that vector, you do Pythagorean's theorem. So you do 21.6 squared plus 22.0 squared, then square root that. If you do that, you're going to get a net force on B of, I got 30.9 when I did that in my calculator. So 30.9 newtons at, and you also need the angle, and you always use the angle, or you should use the angle where you started your diagram. This is where our diagram started. So to find that angle, we're going to do inverse tangent of opposite over adjacent. Opposite leg versus adjacent leg. So you got 22.0 over 21.6. And you get something just a tad bigger than 45 degrees. I got 45.5 degrees. And depending on what kind of direction system they're using, like you could say south of east. You could also say below the horizontal if you wanted to. But there you go. One last thing, they might go and say, okay, let's say that charge C and charge A are fixed, and then you let charge B go. Okay, well, he's going to go shooting off this way. Question is, what's his acceleration, right? So you got the net force acting on charge B. Well, how would you find his acceleration? Well, I'd have to give you one more bit of data. You'd have to know his mass. So if I gave you his mass and you know net force acting on him, you can use the tried and true net force equals ma, Newton's second law of motion. So that would get you the acceleration. So there's an example of a two-dimensional example of using Coulomb's law to find the net force acting on a charged particle. I hope that example was helpful, and thank you very much.